As we begin second semester calculus, it would be important for us to talk about the difference between the content in the two semesters. The first semester was all about the derivative, differential calculus, and it describes rate of change at given points. All about rate of change. And we did a lot of studies of motion with this. In integral calculus, which is what we're heading into this semester, we are studying how instant changes can accumulate. So what we're looking at is accumulation. And both of these are with respect to time. So when we look at how things accumulate over time, what we're looking at are area and volume. And we're going to start today with talking about area. Well, we're going to let this graph, it looks like an XY graph, but we're going to use RNT because we are talking about, we're going to be talking about motion a little bit. Now, if you remember, the distance that an object travels is its rate times the amount of time that it is traveling. Now, let's say that we only want to measure how much distance I have traveled between the 7th and 9th hours of driving. It's a long trip. And we're going to say that velocity is constant at 75 miles per hour. So the speed control has been set. And we'll say that this is about 75. And we know that velocity is a rate of change. Well, if the velocity doesn't change, we have a horizontal line, and this graph here represents the amount of distance. The whole thing represents the amount of distance covered. But let's look at this. What we have is a rectangle. And here our time, this is the width of our rectangle. And our rate right here, this is length. So we could say that to find how much area is in that rectangle is the same as the amount of distance that I have traveled. So my area here is equal to distance, which is equal to 75 times 2, and I have traveled 150 miles. So what we're going to be looking at is how to accumulate area, you see all this area here, under a particular curve and between 2 points in time. So let's take a look at this one. We don't always drive the same speed on whatever road we are. We have to start at 0 and we end at 0, and it goes up and down in between. If you notice this one, my velocity function is curved. So the distance that we traveled here is not the area of a rectangle. So since velocity varies, the area of the rectangle is not equal to distance. We can't use the area of a rectangle to give us an exact distance. So what we're going to do is learn how to handle this. So what we're going to do is a method called rectangular approximation. And we will be dividing the region into rectangles. So let's just say, to make it easy, we're going to divide this one equally in two. And we have two smaller rectangles, and we could estimate. So if you took the area of this rectangle and you added it to the area of this rectangle, then we would have a pretty fair approximation of what the area would be. So let's do one with a problem, and we have three different methods for how to determine the height of a rectangle, and I'm going to show that to you next. Okay, the first method I'm going to show you is called MRAM. Now this first M, stands for midpoint. And RAM stands for rectangular approximation method. Rectangular approximation method. Now, when I give you a problem, I will tell you how many ways I want you to divide up your rectangle. So for right now, what I want you to do is divide this region into 3 equal parts. So right here, so that would be 3 equal portions, or at least 3 equal widths, not so much a portion. So what we're going to do is, since an area of a rectangle is length times width, what we're going to replace length with is the height at the midpoint. And we're going to call width delta t, change in t, how wide is it each rectangle. And in this case, delta t is going to be 1. Now, this whole height at the midpoint stuff, let's take a look at this. So, halfway through this first rectangle is 1/2. Okay, that tells us where the midpoint is. And what we're looking for is how high it is right there, where I just put the dot. So, well, since v is equal to t squared, we want to find the height. And we'll make a little chart here, and I'll help you fill it in just a second. So, the midpoint is 1/2. So when we substitute 1/2 in for t, right up here, what are we going to get? If you substitute 1/2 in for t squared, you're going to have 1/4. Now, the delta t for all 3 of these rectangles, that's 1. So what's the area of this first little spot? Well, width is 1. The height right there, that's what we're using to estimate, is 1/4. So when we multiply 1/4 times 1, you're going to get an area of 1/4. Okay? Now, let's come to this next rectangle. Okay, so the midpoint right here, 3/2. And here we go. That right there, we're going to use the midpoint to estimate the area of the second rectangle. So we're looking for a point exactly halfway between 1 and 2, that's 3/2. And when we substitute 3/2 in for t squared, you're going to get 9/4. We're going to multiply it by the width, which is 1. So here's my area, 9/4. Then we're going to do the same thing here one more time. And this is 5/2, or 2 1/2. We're going to substitute 5 halves in, and that gives us 25 over 4 times 1, 25 over 4. And then when we add all of these together, we get 35 over 4. And whatever our unit is, it's unit squared. So that gives us an estimation. So we're going to take a look at this. Does this look like it's a pretty good estimate? Well, we've got too much over here, and not enough over here, and too much over here, not enough over here. So it probably is a pretty good estimate. So I'm going to show you 2 other methods to find the area using the using 3 rectangles. But we're not going to use the midpoint this time. Next time we're going to use the left side of my rectangle to determine the height. Okay, this time we're going to use the left side of each rectangle to determine the height. Okay, so this first one, and again I'm going to use 3 rectangles, and I'm going to let delta t equal 1. That's how wide each one of those is. Okay, so this is the width. Alrighty. Now, if I'm using the left side of this first subdivision to determine the height of a rectangle, if you substitute 0 in for t squared, you get 0. Okay, so we're not even really looking at the first area. What we're looking at right here is this first area, which I'll just call A1, is 0. So it's a grand overestimation. Okay, now let's look at the second one. Now remember the width of all of these rectangles. They're all 1. Now here, we're looking at the left side of the second part. Okay, now, so that means that our rectangle's height, right here, when you substitute, is 1. So let's look at this. Let's make another chart. So height, width, 1, 1, 1. So for my first one, 0. That means my area is 0. And so for my second one is 1. And you can see, how much are we leaving out? We're leaving a lot of stuff out of here. So probably not the best method to use for estimating the area of this region. But it's a method, so we're going to use it. And then the very last one, we're going to let this left side here determine the height right there. Substitute 2 into t squared, and that gives us 4. So 4. So area, we add all those 3 up, and that gives us 5 units squared. Now if you looked at the previous one, it gave us, I believe, 35 over 4 units squared. That's almost 9. Because the problem here is that this method has left out all of this. So it's basically been cut out. So we've only been using this part and this part to find the area. So in this case, LRAM, not the best method. Okay, so let's discuss what happens with this curve when we look at the right hand. So what I have not told you so far is that right here, this interval notation, that dictates where your curve begins and where your curve ends. So that's very important. Also, if I tell you delta t is equal to whatever number, and for simplicity, I'm letting delta t equal 1, that's the width of our rectangles. So we're going to do the same method. This time, we're going to come over to the right-hand side of each subdivision right here. Now, if you can see where LRAM underestimated, RRAM is going to overestimate. So we're going to have more than we need for this one. So we're going to have height, width, area, and we're going to make a little chart. So the width, that's 1. That is your delta. And your height is going to be whatever you substitute in for t right here. So height is t squared. So I'm going to take my 1 and I'm going to substitute it into t squared, and that's just 1. So I have a square right there if I had drawn that to scale. And for our second rectangle, we're going to come up here and look at this one right there. Okay, now that height, that's not 1. We're going to substitute 2 into t squared. This gives us 4. So 4, and that's 4. And then over here, 3 into t squared, well, that's 9. And 9 times 1 is 9. And that gives us 14 units squared as an approximation. Now, as you can see, using the midpoint as opposed to your left or right side is going to be the best way to estimate this particular area under this curve between the parabola and the axis. But we do have to know how to do all 3 of the methods, and you will be quizzed over all 3 of the methods. Okay, so the more intervals you choose, the better your estimate. It doesn't matter which way you do this. So if we chose to, instead of dividing this up in intervals of 1, and we said, okay, let's do intervals of 1/4 and divide each of these, and we, instead of using 3 rectangles, we used 12 rectangles. So our overestimations wouldn't be so big, and our underestimations wouldn't be so big, and our midpoint would even be more accurate. So the more rectangles you choose, the better your estimate, no matter which method.